Hello, Matt here from chemistrystudent.com. In this video, we're going to look at mass spectrometry and how it can be used as an analytical tool in organic chemistry. We're going to talk about what mass spectrometry can tell us about organic compounds, how fragmentation patterns can help identify structures, what the M+1 peak is, and go through a couple of examples. How mass spectrometry works and its use in determining relative atomic masses of elements has been covered in a separate video. Check the links in the description below. Before talking about mass spectrometry use in organic chemistry in detail, there are a couple of essential ideas you need to be comfortable with. A molecular formula tells us the number of each type of atom in a molecule. For example, the molecular formula of water, H2O, tells us one molecule of water has 2 hydrogen atoms and 1 oxygen atom in. Organic chemistry focuses on carbon-containing compounds, with atoms of carbon forming up to 4 covalent bonds. Relative molecular mass, Mr, represents the mass of 1 mole of a compound. It is calculated by summing the relative atomic masses of all the atoms in a single molecule of the substance. Recap done? Let's go! We aren't going to talk in detail about how the process of mass spectrometry actually works in this video. However, you should be aware that in mass spectrometry, sample molecules are ionized into positively charged ions, and these ions are detected after being deflected in a magnetic field. The greater the masses of the ions, the stronger the magnetic field required to deflect them, meaning we can determine the masses of ions present in a sample based on the strength of magnetic field needed to deflect them. The results are shown on a graph called a spectra. Technically, we actually use something called mass-to-charge ratio, MZ. However, this has been covered in a different video about mass spectrometry. Check the links in the description below. So, on to organic chemistry use. The positively charged ion formed when a molecule is ionized is called a molecular ion. For example, if ethane C2H6 is analyzed, molecules of ethane get ionized and turned into C2H6+ ions. These C2H6+ ions are what get detected in the mass spectrometer. And because they are made up of 2 carbon atoms and 6 hydrogen atoms, each molecular ion would have a relative mass of 30, 2 times 12 from the carbon atoms and 6 times 1 from the hydrogen atoms. On a spectra, this detection would be called the molecular ion peak, and it would be the furthest to the right on the spectra of all other peaks present, as no other ion in the sample can have a greater mass than the original molecule you started with. These molecular ion peaks give you the Mr, or relative molecular mass, of the compound. The interesting thing, however, is that molecular ions that get formed aren't very stable and easily break apart into smaller pieces. These smaller pieces are called fragments. For example, a molecular ion of ethane, C2H6+, will readily break apart and split into 2 CH3 groups. One will have a positive charge, CH3+, and the other will end up as a radical, CH3 radical. The radical we aren't really interested in. However, the positively charged CH3+ fragment will now also be detected in the mass spectrometer, meaning we see a peak in the spectra at 15. This is because the CH3+ ion is made up of 1 carbon atom, relative mass of 12, and 3 hydrogen atoms, each with a relative mass of 1, giving 15 in total. Because the CH3+ ion is slightly more stable than the whole molecular ion, most molecular ions split apart into these smaller fragments, meaning we detect more fragment ions than molecular ions. This is why a larger peak for the CH3 fragment ion is seen in the spectra than for the whole molecular ion. This idea of fragment ions and their peaks can be very useful when analyzing more complicated substances. For example, let's compare the mass spectra of 2 hydrocarbons, A and B, both with a molecular ion peak at 58, meaning the hydrocarbons have a Mr of 58, corresponding to the molecular formula C4H10. If we look at their spectras, they are slightly different. For spectra A, there is a fragment ion peak at 15, almost certainly a CH3+ ion, and at 43, probably a C3H7+ ion. 3 times 12 for the carbons, plus 7 times 1 for the hydrogens, gives 43. This tells us that compound A contains a CH3 group bonded to a C3H7 group. Lovely! For spectra B, there are the same fragment ion peaks as for A, meaning B also contains a CH3 group and C3H7 group. However, there is also a fragment ion peak at 29, a C2H5+ ion. This tells us that compound B can be split apart in different ways to give a CH3 group, a C3H7 group, and a C2H5 group. Because compound A doesn't have the peak at 29, we know it isn't possible to easily break apart A to give a C2H5 ion. Possible structures then might be 2-methylpropane for A and butane for B. This is because for 2-methylpropane, a CH3 fragment could be broken off from a molecular ion, giving possible fragment ions with relative masses of 15, CH3, and 43, C3H7. There is no easy way of forming a C2H5 group, however. For butane, a CH3 fragment could easily be broken off each end of the molecular ion, given fragment peaks at 15 and 43, again CH3 and C3H7. However, the molecular ion could also break apart in the middle, given a fragment that would have a relative mass of 29, C2H5. Explaining why the spectra for B has this extra fragment ion peaking compared to the spectra for A that doesn't. An interesting feature of mass spectrometry for organic compounds is the fact that carbon has naturally occurring isotopes of carbon-12, carbon-13, and carbon-14. Carbon-12 is by far the most common isotope, meaning the vast majority of carbon atoms in organic compounds are carbon-12 isotopes. However, carbon-13 does naturally exist, and a small proportion of carbon atoms in a given sample will contain carbon-13 atoms. If a molecule with a carbon-13 atom in is present in the sample, its relative mass will be 1 higher than the normal molecules that only have carbon-12 in. When detected in a mass spectrometer, molecular ions of these molecules have a relative mass 1 greater than the main molecular ion peak. This is called the M+1 peak and is a naturally occurring peak for organic compounds. Sometimes this peak isn't shown on simple or low-resolution spectra, and as the relative abundance of carbon-13 is much lower than that of carbon-12, the number of molecules containing carbon-13 is very low, meaning the intensity or relative abundance of M+1 peaks are much lower than for the main molecular ion. For example, Ethane C2H6 has 2 carbon atoms in. If both of these atoms are the carbon-12 isotope, the relative mass of each molecule is 30, 2 times 12 plus 6 times 1, given a molecular ion peak at 30. However, if one of these carbon atoms was a carbon-13 isotope with a relative mass of 13, then now the relative mass of that molecule would be 31, given a molecular ion peak at 31. Because only a very small proportion of ethane molecules would contain a carbon-13 atom, the number of molecules with the carbon-13 atom in and a relative mass of 31 would be much, much smaller than the number detected with only carbon-12 atoms, meaning the height, or relative abundance, of the M+1 peak is much lower than the main molecular ion peak. The H2 isotope of hydrogen, deuterium, can also cause an M+1 peak, as again, molecules that contain an atom of deuterium will have a relative mass 1 greater than molecules that only contain the hydrogen 1 isotope of hydrogen. So, to summarize, mass spectrometry is a technique in which molecules and atoms in a sample are ionized, and then the mass-to-charge (MZ) ratio of these ions are analyzed. The results are put onto a graph called a spectra. The peak to the far right on the spectra is called the molecular ion peak and corresponds to an ion of the whole molecule. The MZ value of this peak is the same as the MR, or relative molecular mass, of the compound. Molecular ions are unstable and easily break apart into smaller ions, called fragments. These fragment ions are also detected in a mass spectrometer and can give useful information about the structure of a given compound. Carbon-13 and H2 isotopes in a sample cause an M+1 peak that corresponds to molecular ions, or fragment ions, that contain one of these isotopes in and have a relative mass 1 greater than ions that don't. I hope you found this video helpful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.